Good day. Thank you for joining this webinar on the irrigation of citrus, which will focus on understanding the basic principles that make part of setting up an irrigation schedule. My name is Coenraad Fraenkel. I am the Extension Manager for the Western and Northern Cape with CRI. Water is a scarce resource, and more pressure will be experienced in the future to increase the water use efficiency and nutrient use efficiency. It's not only about saving water, but increasing the amount of fruit produced for every liter of water used. These days, most of the nutrients are applied through the irrigation system, and if the efficiency of the irrigation is questionable, the nutrient application will also be questionable. What we will speak about today really boils down to the effective management of soil moisture. At the end of the day, we need to get to an answer of when and how much to irrigate and plan or adjust accordingly. So what is soil moisture? It's not only the water in the soil, but the balance between the water and the oxygen in the soil pores. Here you can see from the illustration that roots would move between particles, and in between the particles would be a good balance of soil water and oxygen. The size and the amount of pores in the soil is determined by the texture and composition of the soil. There are larger and less pores in the sandy soil versus smaller but more pores in the clay soil. This will have an effect on the amount of water the soil can retain, which is termed the water holding capacity. It is expressed as the amount of water in millimeter that the soil can retain after all freely drained water has been removed from the soil. This is expressed over 1 meter depth, which is then millimeter per meter. There is a perception that the texture alone determines the water holding capacity, but the ratio of different sand grades, let's say fine sand or medium sand, have a significant effect on that water holding capacity due to the varying pore sizes. Why is this pore size important? The smaller the pore spaces, the stronger the soil particles will absorb and hold onto that water in the soil. The result is a higher water holding capacity. Larger pore spaces, like in sandy soils, will result in lower water holding capacities. Other factors that might also have an effect on the water holding capacity range from coarse fraction in the soil, which decreases the water holding capacity, or organic matter that might also retain water to a lesser extent than the soil particles, but in very organic soils it will also play a factor. Here we are not referring to mulching, but we're referring to organic matter. Let's look at these three examples. In photo 1, there is a major difference between the topsoil and the subsoil texture and structure. It's also a very shallow profile. The profile hammer is roughly 30 centimeters. A higher clay content and stronger soil structure in the subsoil will increase the water holding capacity, but also decrease the impermeability of the soil, resulting in a possible fluctuating water table that might push up into our root zone. In photo 2, which we have a higher organic matter in the topsoil, which also has a very high silty content, or a loam soil, it's overlaying a higher clay subsoil with a strong structure. The water holding capacity of the top organic horizon might be less than the underlying clay layer, but the water availability for plant uptake will be much higher than that clay subsoil. In photo 3, you can see that in certain soils, especially in alluvial floodplains, a soil profile might be made up of different layers of sand and clay and silt, which forms really complicates the hydrology. It really makes it very difficult to manage the soil moisture due to the varying textures and water holding capacities. In this instance, the correct soil preparation before establishment is critical to make sure that it is actually a manageable soil. There are a few figures available for a rough estimate of the water holding capacity published by Mayberg in 1993. But it is worth it to get it analyzed from a physical lab. The water holding capacity might in some cases vary from one area in an orchard to the next. Try to subdivide orchards before establishment to accommodate the varying differences in water holding capacities. Using a graph to illustrate the correlation between the soil texture and soil moisture conditions, the dark blue area at the top is the gravity water, or which is typically leaching or deep drainage water out of the root zone. The dark blue line represents the field water capacity line, which after deep drainage of water, the water that is left in the soil profile, the readily available water and the hygroscopic water represents. The white area is typically the readily available water. The brown line being the permanent wilting point. At around 40 to 50% of plant available water, the plant will experience a degree of stress. The light blue area below the brown line is our hydroscopic water. That is water that is not available to the plant and is strongly absorbed by soil particles. The sandy soil on the one end of the graph have a greater pore size and thus less porosity with a greater amount of gravity water, which is leaching water. Thus also closer to a wilting point and less available water to the plant. The clay soils on the other side of the graph has a higher amount of hygroscopic water, which is not available to the plant, and if it gets wet, it stays wet for a longer period. Interesting enough, the water holding capacity of the clay soils might be higher than sandy soils, but due to the higher amount of hygroscopic water, the plant available water might be less than expected. The harder the tree needs to work for this water, the smaller the fruit might be. Loamy soils, which is typically in the center of this graph, has a good balance between pore sizes and thus the highest plant available water. During different phenological stages, different depletion rates of readily available water is allowed without having a negative effect on fruit quality. It should be mentioned that depletion rates are not implying an uncontrolled stress, but rather good soil moisture without having a negative effect on fruit quality. It is important to note that in cell division, which is between October and November, a 30% depletion of plant available water is allowed, thus leaving 70% of plant available water in the soil. If any stress occurs during this phase, the effect on fruit size will be irreversible. Now that we've covered the water holding capacities of our soils and the allowed depletion rates during specific phenological stages, we need to understand where our roots are in this dynamic soil reservoir, as this will determine our placement and our quantity of water to secure the ideal soil moisture. As Dr. Raad has mentioned on many occasions, making a profile in an orchard is extremely valuable to capture data to assist in your decision making, before establishment but also after establishment in non-bearing and bearing orchards. The root depth and root width is very important to determine how large the reservoir is that should be filled with water to restore the soil moisture balance. Noting the root distribution without doing a soil profile is a risk. The root distribution varies between tree ages, rootstocks, irrigation systems, etc., and is also influenced by the impermeable clay layers, excessive wet conditions, etc. The spacing of the roots in the tree row, as well as the lateral spacing of the roots, are equally important. As mentioned, the water holding capacity is expressed as millimeters per meter. Let's use an example. If we use the very coarse sandy soil as an example, which was 50 millimeters over a 1 meter depth, if the effective soil depth is up to a depth of 60 centimeters, the amount of water that could be plant available in the soil will have to be reduced with 40% or to a depth of only 60 centimeters. So, when digging a profile, note the following. To what depth is 80% of the feeder roots? This is in most cases not deeper than 40 to 50 centimeters. How wide is 80% of the feeder roots? And at what depths do impermeable layers occur, or add 20 centimeters to the bottom of the effective profile if there is not an impermeable layer? This will be the buffer zone in the future. When irrigating, there needs to be focus on the root zone and the buffer zone, not only on the root zone. The buffer zone holds water at a depth away from evaporation and during heat waves provide a source of water that takes pressure off irrigation applications. This does not imply that the buffer zone should constantly be saturated with water. Producers tend to over-irrigate this buffer zone, but remember, soil moisture is a good balance between water and oxygen. Due to the more piston type of action that micro-irrigation creates, the root distribution tends to be in a more uniform square area around the tree. Digging a profile pit will definitely provide more information of where the roots are and how deep they are. The root distribution of roots under drip irrigation is more globe-like and with various positions around the tree. It might vary from 6 to more dripper pots. Once again, it is critical to open up a profile and note the root distribution. It does not make a difference what irrigation system you have, may it be micro or drip irrigation. It is equally important to be aware of how long it takes for an irrigation application to fill up the reservoir without leaching beyond the buffer zone. Irrigate and make a profile pit an hour after irrigation has stopped to see what time it takes to wet the root zone and what time it takes to irrigate to refill the buffer zone. Next, we will speak about the use of weather data. Site-specific weather predictions are critical in our decision-making process. Automatic weather stations provide accurate information regarding radiation, relative humidity, temperatures, wind speed, to name a few. This is all used to calculate the predicted evapotranspiration, or ETO, of a specific site. ETO refers to the evapotranspiration, which is the combination of evaporation from the soil surface and plant uptake out of the soil, termed transpiration. The ETO refers to the potential evapotranspiration from a short grass reference crop from the Penman-Monteith model. Crop coefficients for a specific crop and site should be developed over time. It is an indication of the amount of water the orchard needs during the same period what the ETO represents. It accounts for tree characteristics, which is typically canopy size, plant density, and effective canopy size. Average long-term ETO values for the different production areas in South Africa have been generated by SAPWAT, but it's advised that site-specific weather data be used. These values can be used as a good starting point. These values are available on request or can be found in an article that was published by Pieter Raad, Chris Milan and Tiens Vaarmeyer in the SA Fruit Journal of February-March 2020. Vaarmeyer and Taylor in 2019 published crop coefficient values for different production areas. The canopy size refers to 70% in the top of the table, which refers to 15-year-old or older trees, the 50% 10 to 15-year-old trees, and 30% to younger than 10 years but bearing trees. Note that the values vary between drip and micro-irrigation values. It is important to note certain criteria of irrigation system. This will have an effect on the scheduling calculations and the efficiency at which the irrigation system can be used to manage the soil moisture. The application efficiency refers to the percentage of the irrigation water that actually reaches the soil and the roots. Flood irrigation is roughly 60% efficient, micro irrigation 80%, and drip irrigation 90% respectively. A decrease in this efficiency is mainly due to the conditions that favor evaporation and decreases water penetration into the soil. The spacing of the sprinklers and the drippers refers to the distance between the sprinklers, which has an effect on the amount of emitters per hectare, which is used to irrigate and replenish the soil moisture. The delivery rate is the volume of water that passes through an opening of the sprinkler or dripper at a given pressure. This delivery rate should be checked in the orchard during the season, as this may vary dramatically. Place a bucket under a dripper or a sprinkler for a minute and translate that back to a delivery rate of liters per hour. The wetted width refers to the amount of area that is wetted during an irrigation. A profile pit after a full-length irrigation might be needed to capture this information. To provide a theoretical example of calculating an irrigation schedule, the following is used as a baseline data for an orchard. This example is described in detail in the article that was published in the SA Fruit Journal in February-March 2020. This is a mature orchard in Letsatele. 70% of the orchard is covered with leaf canopy. The soil texture is a loamy sand. The tree spacing is 7 meters by 3 meters. After a soil profile investigation, the effective root depth was established at 40 centimeters. The wetted width is 40% of the soil surface. The month that we want to calculate the irrigation schedule is in January. The lab analyzed the soil and the water handling capacity of 80 millimeters per meter is reported. January is in cell expansion, and according to the phenological stage, 40% of extraction of plant available water is allowed. The long-term ETO value for January in Letsatele is 4.3 millimeters per day. It's a micro-irrigation, so the application efficiency is 80%. The delivery rate of the sprinklers is 30 liters per hour, according to the design, and the sprinklers are spaced 3 meters apart, thus a sprinkler between each tree. To calculate the amount of water needed to fill the profile to field water capacity, the following calculation can be done. The water holding capacity, as from the lab results, times the root depth, which is noted in meter from a profile investigation, times the percentage extraction which is allowed from the phenological stage, which is in cell enlargement in January, times the wetted area, which we also gathered from field observations. This comes down to 5.12 millimeters or 51 cubes per hectare, which is needed. To calculate the delivery rate of the irrigation system, the following calculation can be done. Sprinkler delivery rate, which you receive from the supplier, times the number of emitters per hectare as from the design, divided by the percentage of the wetted area, which also you get from a profile observation. This comes down to 3.57 millimeters per hour. To calculate the length of irrigation needed to supply the required water, the amount of water needed as from the previous calculation divided by the sprinkler delivery as from the previous calculation comes down to 1 hour and 25 minutes of irrigation needed. How often do we need to irrigate to apply this amount of water? That is the amount of water needed as from the previous calculation divided by the evapotranspiration as from the long-term average, that's SAPWAT table, divided by the crop coefficient from Farmeyer and Taylor, divided by the system efficiency, which in this case was micro 0.8 or 80% efficient. It comes down to 1.6 days or rounded to 2 days. Thus we need to irrigate for 1 hour 25 minutes every second day. Important to note that the time when the irrigation is applied is also extremely important. The best time to make an application is early in the morning or late afternoon. Applying 1 hour 25 minutes in the middle of the day would not be effective. All these calculations that we've presented now is theoretical, and using probe data and field observations can assist enormously in fine-tuning your schedule. If you are ready for the next step to incorporate probe data into your decision making, the following is of importance. To effectively place one's probes on a macro scale, one needs to keep the following in mind. Understand your soil distribution or the variability of the soils. Soils vary as mentioned earlier. Placing a probe in a non-representative area will not be effective. Group your soils together into management zones as indicated in this image in the right hand corner. This will have an impact on nutrition, irrigation, and other aspects. A probe should represent a specific management zone and be calibrated according to soil type. Micro sprinklers should not be placed directly next to the stem when trees have reached full bearing. The micro sprinklers should be placed halfway between two trees. The probe, in turn, should be placed between the edge of the tree canopy and the tree stem. Make sure that the same soil is used for the slurry and that the probe depth will monitor the root zone and the buffer zone. In full bearing orchards, the drippers should be placed halfway between the stem and the edge of the canopy. The ideal is that the drippers be pegged as to not have movement of that dripper pots. The probe should be placed 20 cm from the dripper in the root zone. Be sure not to place it directly underneath the dripper or at the edge of the dripper pot. Under the dripper, the conditions will be too wet, and at the edge of the pot, there tends to be an accumulation of salts that reduces root activity. Make sure that the probe length should be able to monitor to a depth below the buffer zone. This is valuable to monitor deep drainage, leaching of salts, and over-irrigation when you need to manipulate either your salts or leach and so forth. The reality is that although the soils have been classified and grouped together, the in-orchard variability will also need to be managed. When very distinct lines are observed in the NDVI, which we call normalized difference vegetative index, the chances are that an irrigation related problem is occurring. The pink dot on this image indicates where the probes are installed to monitor the soil moisture content. It is recommended to do field observations or field tests in both zones, as well as making profile pits to see what the root distribution is like. During the field observations, rate the soil moisture as described in the table from 1 to 5, 1 being bone dry and 5 being very wet. Make observations at 20 cm depth intervals, 0 to 20 cm, 20 to 40 cm, and 40 to 60 cm. Note the depth of infiltration and if runoff occurred. This can be done via soil auger if the root distribution have been captured in the past. Important to also note the date and time of observation so that it can be correlated with probe data. Try to make your field observations at the beginning of a week or before the start of an irrigation cycle. On the right hand of that table, the rough estimate on what is the percentage of plant available water that is still left in the soil with each index level. The area in green on the NDVI indicated a 4 out of 5 during the field observation. To calibrate yourself with the probe data, and relevant field observations, 5 out of 5 is above the top line of the probe data. 4 out of 5 is on the top line of the probe data. 3 out of 5 in the ideal zone, 2 out of 5 on the bottom line, and 1 out of 5 below the line. The probe data at the time of the field observation indicated a 3 out of 5 on the probe graph. This indicates that the top line on the probe data is set too high and might have to be adjusted downwards to match the actual observation in field. In summary, determine the water holding capacity of your soils. Be sure to take the percentage of allowed extraction per phenological stage into account during your calculations. Use the formulas provided and calculate the delivery rate of the system and calculate the length of the cycle needed to replenish the soil to field water capacity. Use the ETO and crop coefficients to calculate the period between cycles and make sure that your probes are placed the best macro and micro position. Finally, use regular field observations and probe data to avoid over or under irrigation during the season. Thank you for listening to this webinar. If you have any questions or comments, please send them through to us on our emails or contact us directly on our telephone numbers.